Okay, here we are for the last part for today, and that is going to, I'm just going to reiterate that on the last example we only used one logarithm in the expression to straighten out the data. When you use one logarithm, we know that the model that it came from was the exponential model. So, and I said we go back to the power model, so let's actually do that. So mathematically speaking, we had the power model, and the power model was y equals ax to the b, and I'm going to take the log. I told you that we can straighten it out with powers and with cubes and so forth. We can use powers and roots to straighten it out, but sometimes logarithms work even quicker and better. So we're going to see what happens if we take the log of both sides on the power equation. So taking the log of both sides using the rules of logarithms. And this time we have log here. ln of a is just a constant. And we have a b, so we have another constant. So we call that constant 1 and constant 2. But ln of x. Notice at the end of our story we have two logarithms. So sometimes when we start with the power model, and you end up with two logs. So if you find that two logarithms are required to straighten out your data, you know it's coming from a power model. One logarithm will straighten it out if it's an exponential model, but two logarithms are needed for a power model. So let's jump to the last example, and I will assign for you the page in between. So the assignment will be this one that you can work on after the video, and you'll be able to do that. And now we'll look at an example that comes from a power model where two logarithms are required to straighten it out. So in this scenario, the last one, and it's talking about a planet, they actually found a body in our solar system. They call it Eris, or Eris, and is it a new planet is the question. So they're studying this planet, and they did that by looking at the relationship from all the planets we do know, and they found the period, which is how long it takes a planet to go around the sun, which is its year, in the distance it is from the sun. And we're going to do our distances in AU with the astronomical units. An AU of 1 is the distance of the Earth from the sun. So the Earth is 1 AU away from the sun. So using this time to go around the sun once and the distance from the sun of the planets, and it didn't even show up, but it is somewhat curved. So you can put some curved dots on your graph that looks blank. So there's curved dots, and from that they attempted to straighten out the data by taking the ln of the period and leaving this the same, the distance in AUs. And guess what? It didn't straighten it out. It curved it the other way. So what else could we try? Again, a lot of trial and error here. So we're going to do ln of the period, and then we're going to do ln of the distance as well. And when we did that, voila, straight as an arrow. Not straight as an arrow, but much more straight. Looking at mini-tab on the back, let's come up with the relationship. So we're looking at these numbers here. So I'm going to come up with the equation for a relationship between period and distance. So I'm going to take the ln of what was on the y-axis equals some constant a plus some slope b, and then ln of the distance or whatever was on the x-axis. So now adding meaning, I do ln of the period of the planets equals the y-intercept from Minitab plus 1.49986 ln of the distance. So it took ln of both variables. Notice the slope is in front of this variable. So the question is, the planet Eris is 102.15 AUs. 102.15 AUs away from the sun, so I want to predict its period. So I'm going to use this relationship to do that. So I'm looking for period, so ln of period remains equals 0.0002544 plus 1.49986 ln of 102.15. Alright, so putting all that in, I get ln of period equals 6.94. So you can tap that in, use your ln button, and you'll get that. So again, this is base E, so this raised to that equals this. So the period equals e to the 6.94, and we get, when you plug that in, the period is 1032.77 years. That's how long it takes this perhaps planet to go around the sun. It's quite distant from the sun. Alright, so how is our S for that one? Let's go and see. S is very, very small, so it's a good choice. So according to the data, that is a good choice and a good predicting line. Alright, the residual plot has some aspects to discuss. So let's look at that. And I'll end our part for today, and you can work on your problem if there's time. If not, that's the only thing for homework I would have. So, do we expect the prediction in part C, which we had 102? For 102, we got that 1032.77 years. Do we expect that? Do we expect that to be too high or too low or just right? So, what number were we putting in for distance? We were putting in the distance was 102.15, but we were required to take the ln of that. So when you took the ln of 102, it came out in the middle of our calculation right here. It says ln of the period is 6.94. So what would be, we're trying to find the distance from this example. So we had 102, but we need to think about it in ln's. Oh yeah, so in ln's it was 6.94. So where would 6.94 be on this chart? So we'd have to go out 4 to 5 to 6, so extrapolating a little bit. 4, 5, 6, 7, not quite to 7. So if we're following this pattern, this may continue. If it does, and out here we're still way above the residual line, that means our prediction line would be below what our prediction line would be below what the true value should be. So notice it's above the prediction line. This is the prediction line. That's the numbers we fed it into, and we got out 1,032 years. So this would be above, but we don't know for sure because this pattern could have went right back down. So therefore, we're making a major guess on this one. So what should I say for that one? Let's say what I said last year. I said, assuming the residual plot is above the prediction would be too low, and that's clear. Here's the prediction line, here's the observation, so therefore it is below. All right, but we have to make the assumption that the residual plot would continue like this. All right. All right, I'd like you to go ahead and go back to the one that I skipped, the one about population, and answer the questions there, 1 through 4, about that situation. And that's all for me today. I'm not sure how much of this class fit, how much of these videos fit into your class, but assuming that they all fit, then you can go ahead and do that one problem in class or as a homework problem. If you didn't get to finish these videos, we will finish them in person together tomorrow. All right, that's it. Carry on, class. Goodbye.